Have you ever encountered a problem so overwhelmingly complex that even the most powerful supercomputers would take eons to solve it, far longer than the age of the universe? It is a fascinating thought to consider whether there is a fundamentally different way to compute that could overcome these seemingly impossible barriers. Precisely defining quantum speedup means identifying when a quantum computer can solve a specific computational problem demonstrably faster than the best-known classical algorithm available. This is not about a quantum machine simply running a classical program a bit quicker. Instead, it represents a fundamental algorithmic advantage, often leading to a reduction in the number of computational steps required to reach a solution. The core reason behind this potential speedup lies in the unique properties of quantum mechanics itself, specifically superposition and entanglement. Unlike classical bits that can only be 0 or 1, quantum bits, or qubits, can exist in a superposition of both states simultaneously. Entanglement further allows multiple qubits to become interconnected, sharing a fate regardless of distance. These phenomena enable a quantum processor unit, or QPU, to explore many possible solutions simultaneously in a way that is fundamentally impossible for a classical computer. This inherent quantum parallelism transforms the very nature of how certain problems are tackled, allowing for an exponential or polynomial reduction in complexity for particular tasks. To measure this speedup precisely, we do not just compare raw execution times for a single instance of a problem. Instead, we analyze the theoretical algorithmic complexity using mathematical notation, often referred to as Big O notation. This method describes how the runtime or resource usage of an algorithm scales as the size of the input grows. A true quantum speedup implies that the quantum algorithm's complexity class is provably lower than the best-known classical algorithm for that problem, meaning it scales much more efficiently with larger inputs. A prime example of this theoretical advantage is Shor's algorithm for factoring large numbers, which offers an exponential speedup over the best-known classical algorithms. Another is Grover's algorithm for searching unsorted databases, providing a quadratic speedup. These are not incremental improvements but rather profound shifts in computational efficiency for specific, often foundational, mathematical tasks. The concept of quantum advantage is a related term, typically referring to the experimental demonstration that a quantum device can perform a computational task that no classical computer can perform in any reasonable amount of time, even if the task is not necessarily useful. Understanding quantum speedup means appreciating that it is not a universal accelerator for all computations, but rather a powerful, targeted tool that fundamentally redefines the solvability of certain intractable problems. It is a precise algorithmic advantage, rooted in the quantum nature of reality, that promises to unlock solutions in fields ranging from materials science to cryptography, transforming our capabilities for complex computation.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.